Good morning, everyone. Myself Shomujit Nayak from third year EC department. Today, I have made a Python-based project of digital communication, which is based on sampling, aliasing, and reconstruction. And here you can see the my GitHub link where you get all whole my project. And I paste the code of Python in Google Colab and here you can see the code and the output graph. So I wanted to actually see aliasing happen when aliasing happen instead of just reading a book, reading about it in a textbook. So I built this, sampling a signal three different ways and watching where it breaks. Let me show you. Um, I made a sample two tone test signal which is uh, 10 hertz and 20 hertz. This to add it together. Nothing fancy. The reason I use two tones instead of one is actually kind of important. With one sine wave, you cannot really prove aliasing happened. You had just see a slower wave and have no way to know it's fake. With two tones, there is an advantage that if one of them folds down and lands on the top of the other, you can catch it re-handed, and that's the whole trick. And you can see the below three cases. One is the case one is mm above the Nyquist ridge. First 50 hertz above the limit, and yeah, exactly you had expect the reconstruction signal basically sits right on the reconstruction signal, and blue color represent the reconstruction signal. Reconstruction signal basically sits right on the top of the original. But here is a small thing I noticed that I didn't expect the going on. The error is not actually zero even here, and you can see the error plot. Uh, and it was the at the edges of the graph, then in the middle, and it took me a second to figure out why. It is because of my reconstruction formula. Sync interpolation is only perfectly accurate if you sum infinite samples. I only have a finite window. So the edges get a little sloppy, not aliasing, just a side effect of not having infinite data. Okay. Mm, Now move on to next case. The case is quite interesting. At Nyquist date, and this is my one is my favorite honestly because I didn't plan for it. 40 hertz, exactly the Nyquist rate. On paper, this should be fine, right? Bare minimum. Okay. Uh, but look at this. The 20 hertz tone basically disappears in the spectrum, barely a bump. Here you can see, barely a bump. I stared at this for a bit before I realized what happened. At exactly 40 hertz, my samples kept landing on the zero crossing of the 20 hertz every single time. So as far as the samples are concerned, that the wave mm, sampler concern that the wave might as not exist. That's a real lesson here. Lesson here. Meeting the Nyquist exactly is a technically not a safety margin. In real system, you always sample a good bit above it. Okay. Now move on to the last and but not the least. Below the Nyquist case. Now the one you are actually here for 30 hertz. below Nyquist did. And here you can see the graph of the three. You can see the Nyquist below the Nyquist did graph, and this is magnitude spectrum graph, and this is reconstruction error graph. So reconstruction just fall apart here. It doesn't even look like the same signal anymore. Just one slow wobble. So I didn't the math by hand to check what should happen. The foldback formula says the 20 hertz tone should alias down to 10 hertz, and when I check down the actually FFT output, yeah, that exactly what the energy piled up. Right on the top of my real 10 hertz component, that's aliasing. Two completely different frequency becoming impossible to tell apart once you one undersample. Okay, so this is my whole project on the basis of the sampling, aliasing, and all reconstruction. Thank you so much, everyone.